For a long time, humans have pondered the possibility of alternate universes and the nature of existence beyond our own world. Thanks to the James Webb Space Telescope JWST, the most advanced observatory ever built, this question may soon be answered. By observing Proxima Centauri, the star system closest to us at just 4 light-years away, scientists have detected unusual signals emanating from one of its planets, Proxima B. These signals, described as artificial illumination, have fascinated the scientific community. But what do they mean? Could these lights suggest the presence of intelligent life on that planet? Join us as we explore JWST's groundbreaking discovery of city-like lights that could transform our understanding of life beyond Earth. Currently, Earth remains the only known planet to harbor life. Since the dawn of civilization, humanity has wondered whether life exists elsewhere in the cosmos. To investigate this, American astronomers Jill Tarter and Thomas Pearson launched a search for extraterrestrial intelligence SETI project in 1984. SETI aims to detect extraterrestrial radio signals, as radio waves can travel vast distances and are easier to pick up by the 42 radio telescopes that make up the specialized Allen Telescope Array in California's Sierra Nevada mountains. However, no confirmed extraterrestrial signals have been found so far. The deployment of the James Webb Space Telescope has since intensified efforts to study exoplanets orbiting distant stars. As the largest space telescope ever launched, positioned about 1 million miles from Earth and equipped with highly sensitive instruments, JWST holds immense potential for revolutionary discoveries. While no exoplanets were known initially, over 4,000 have now been discovered orbiting various stars. According to NASA, the universe could contain millions of such worlds. One promising approach to identifying extraterrestrial life involves detecting signs of alien vegetation. The Galileo spacecraft en route to Jupiter once turned its instruments toward Earth and detected a clear signal of vegetation by observing the vegetation red edge, a biosignature marked by a unique combination of red and infrared light reflected by plants. A planet covered in dense foliage like Earth would produce a strong, identifiable red edge signal. JWST aims to measure this red edge on distant Earth-like planets located in the habitable zones of their stars, offering critical clues about the conditions beneath their atmospheres. When sunlight passes through a planet's atmosphere, certain frequencies are absorbed by particles and molecules, creating unique spectral fingerprints detectable by JWST. This spectroscopy can reveal the atmospheric composition and whether conditions might support life. Life as we know it could exist on Earth-sized planets with atmospheres containing oxygen, nitrogen, and carbon dioxide. Detecting unusual compounds, such as chlorofluorocarbon CFCs, chemicals used in refrigeration and cleaning, will be a strong indicator of technological activity, as these compounds will be clearly visible to extraterrestrial observers scanning Earth from afar. Similarly, if JWST were to find CFCs in exoplanet atmospheres, it would suggest the presence of advanced civilizations. However, extraterrestrial life might not resemble terrestrial organisms. Extremophiles, microbes capable of surviving harsh environments like extreme heat up to 250 degrees Fahrenheit or highly acidic conditions, pH below 3, could appear alien to us. While planets with extreme temperatures or acidity may be less likely to support complex life, planets similar to Earth, with stable orbits and temperatures that allow liquid water on their surfaces, remain the most promising candidates to search for life initially. Our Sun is classified as a yellow G-type star. These stars are relatively rare and tend to have shorter lifespans. However, in the universe, planets orbiting red dwarf stars, stars that are more common but have lower luminosity and cooler temperatures than the Sun, are more frequently studied. The longer lifespans of red dwarfs provide extended time frames that could allow life to develop and complex organisms to evolve. About 40 light-years from Earth lies the TRAPPIST, one planetary system, the focus of the James Webb Space Telescope's JWST first mission. The system orbits a calm red dwarf star and hosts 7 Earth-sized rocky planets. 3 of these planets reside in the so-called habitable zone, where liquid water could potentially exist on their surfaces. Despite TRAPPIST, one being smaller and cooler than our Sun, it emits light somewhat similar to sunlight on Earth. Because its planets orbit very close to the star, this system offers a promising chance to detect signs of civilization, such as city lights. Another intriguing target is Proxima Centauri, a red dwarf star just 4.25 light-years away from the Sun. Proxima Centauri is much dimmer than our Sun, so a planet would need to orbit much closer to support life. In August 2016, astronomers discovered Proxima B, a planet about 1.3 times Earth's mass, located within its star's habitable or Goldilocks zone where light intensity is suitable for liquid water. Proxima B orbits extremely close to its star, just 4.66 million kilometers away, exposing it to intense solar winds that might strip away its atmosphere. This proximity suggests it may be tidally locked, always showing the same face to its star, much like the Moon does with Earth. Proxima Centauri itself has only about 18% of the Sun's mass and emits roughly 5% of its brightness. While Proxima B might appear to be a barren, scorched world, liquid water could still exist if the planet has an atmosphere thick enough to retain heat. The energy it receives from its star is about 65% of what Earth gets from the Sun, which means the environment may be less hospitable to life, but not impossible. Its tidal locking results in permanent day on one side and permanent night on the other, causing extreme temperature differences. Additionally, Proxima B faces almost 3 times the high-energy radiation Earth does, including X-rays and ultraviolet light, due to frequent solar flares from its star. Without a protective magnetic field like Earth's, sustaining life could be very challenging. However, if the planet has a strong magnetic field and volcanic activity to replenish the atmosphere, it might retain an environment where life could exist. Because we currently lack detailed information about Proxima B's volcanic activity or magnetic field, it is still uncertain whether it holds a substantial atmosphere. Since an atmosphere is often linked to the presence of seas, and both are indicators for potential life, there is significant hope to determine if Proxima B supports a complex biosphere. Speculative ideas suggest the possibility of solar-powered charging stations on the planet's day side, providing energy to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima B has triggered efforts to observe whether it transits its star from Earth's viewpoint. Detecting such transits will allow scientists to measure the planet's size and mass, assess its density, and confirm if it is rocky. During transits, starlight passing through the planet's atmosphere could offer clues about its composition. However, the chance that Proxima B's orbit aligns just right for a transit observation is only about 1.5%, and the star's frequent eruptions make detection even more challenging. As astronomer David Kipping from Columbia University notes, the star's activity adds another layer of complexity to studying this intriguing world. Solar flares cause instability by making a rocky planet absorb sunlight and then emit it as infrared radiation. However, rocky planets orbiting stars like Proxima Centauri emit a distinct type of infrared light. The James Webb Space Telescope, JWST, was specifically built to detect such infrared emissions. Proxima B's infrared signature is key to identifying the characteristics of its atmosphere. Moreover, JWST's infrared detection capabilities far surpass those of the Hubble Space Telescope, potentially allowing it to spot city lights on Proxima B's night side, even if those lights are as faint as Earth's. If artificial lighting on Proxima B exists and is confined to a narrow frequency range distinct from the star's light, JWST could detect it. The planet's day side might also be extensively covered with solar panels, reflecting the star's light. As Proxima B orbits its star, it experiences a consistent day-night cycle with extreme temperature differences. The contrast between day and night temperatures depends on whether the planet is a barren rocky surface or if it has an atmosphere. Without an atmosphere, the day side would emit all the received energy as blackbody radiation, while the night side would be a frozen wasteland. Conversely, a smaller temperature difference would imply the presence of an atmosphere. It would take JWST only 11.2 Earth days to collect enough data to detect potential artificial city lights on Proxima B's dark side, lights that could indicate intelligent life beyond our solar system. Based on current studies, Proxima B might conceal remarkable secrets. Its day side could generate abundant solar energy, and any detected lights might be evidence of an advanced, technologically capable civilization. While the discovery of artificial lighting on Proxima B would be revolutionary, scientists are cautious. Such signals might have multiple explanations beyond intelligent life. The JWST's technology for studying distant exoplanets is still developing, and astronomers are refining their methods. The detected lights could stem from natural sources, such as volcanic eruptions, lightning storms, or unusual atmospheric effects that mimic artificial illumination. Ongoing observations by JWST of Proxima B and other potentially habitable exoplanets will deepen our understanding of their atmospheres and surfaces. Should artificial lights be confirmed, years of further research will be necessary to verify their origin. If these signals do come from intelligent beings, it would represent one of humanity's most profound scientific discoveries. The interest in Proxima B and similar exoplanets extends beyond the search for alien life. It also raises profound philosophical questions about humanity's place in the universe. Finding extraterrestrial civilizations would challenge the idea that life on Earth is unique. It might spark an era of unprecedented global unity, as the awareness of intelligent life beyond our planet could inspire a shared sense of wonder and purpose. Additionally, such a discovery would underscore the importance of space exploration, encouraging nations to invest in technologies that advance humanity's journey deeper into the cosmos. Currently, the search for artificial illumination on Proxima B remains an exciting possibility that could soon help answer the age-old question: are we alone in the universe? As JWST continues to deliver more detailed data, the hope of finding signs of advanced life grows stronger, bringing us closer to solving one of science's greatest mysteries. If Proxima B does harbor an advanced alien civilization, that discovery could lay the foundation for breakthroughs in astrophysics, planetary science, and interstellar communication. Future generations of researchers and explorers may confirm what once seemed unimaginable, that life in its many forms may be far more common throughout the universe than we have ever dared to believe.